Bonsoir.
Good evening, welcome to you all. I'm Marcel Weber, I'm the director of the philosophy department of the University of Geneva. I'm very happy to extend a warm welcome to you for this conference. This evening it will be a great pleasure for us to listen to Fay Dowker, professor of theoretical physics at the Imperial College in London. She will be speaking about the science of time. This conference is dedicated to Stephen Hawking, the physicist who passed away very recently and who directed Fay Dowker's PhD thesis in Cambridge. Now, it may seem strange for the philosophy department to invite physicists, but when we wonder about fundamental notions such as time, which is a common object of research for both philosophers and physicists, it is very important for us to encourage such collaboration. From the point of view of philosophy, the fact of knowing whether time belongs to the outside world, researched by physics, or whether it is part of the internal rules studied by philosophy, is something that shouldn't be taken for granted. Nonetheless, because of its colossal scale in the cosmos, and because of its mysterious nature within us, time is something that is fascinating for both these reasons. It has therefore captivated Kant, Leibniz, as well as Stephen Hawking in the past. Its mysterious nature continues to nourish the work of physicists such as Fay Dowker, as well as contemporary philosophy, and I hope that it will be a source of wonderment for us in the future. With no further ado, it is a pleasure for me to give the floor to the organizer of this evening, my colleague Christian Wüttrich, professor in science philosophy at the philosophy department, and he will be introducing us to our speaker tonight, Fay Dowker.
Merci beaucoup. I will change to English in case you want a simultaneous translation. Now might be the moment to put that on. Hector Berlioz once said, "Time is a great teacher. Unfortunately, it kills all its students." In spite of that, philosophers and physicists have studied time and space for as long as they have been in business. In fact, the philosophy of space and time constitutes a central part of the philosophy of physics, which in turn constitutes a central part of natural philosophy. That is, the philosophical consideration and reflection of the natural world that we find ourselves to inhabit. Natural philosophy in turn forms a central part of philosophy more general. Thus, philosophy of space and time holds a rather important place in philosophy, which is also justified by the fact that many philosophical accounts or theories rely implicitly or explicitly on the nature and even the existence of space and time. It is precisely the nature and indeed the very existence of space and time that is the central topic for the philosophy of space and time, of course. More specifically, the philosophy of time is concerned, for instance, with questions such as, does time pass? It seems one of the most obvious features of the world as we experience it, that time passes, but it's a highly non-trivial and very deep philosophical question to consider whether that passing of time, that flowing of time, is part of the objective physical reality outside of us and independent of us, or whether it rather only arises as for us, for human sentient beings like us, to interact with that physical world. Also, you might think one of the most important things is that the present and the present things presently existing, are the only things that exist. Past things have existed, but clearly no longer do, and future things will exist, but they do not yet. But is that so? Is it only the case that the present is real, or is the past and the future just as real, perhaps? Is time finite or infinite? Does it have a beginning or an end, or both? We also realize that many things, many physical processes around us, like the very simple things as melting of an ice cube in a glass of water, seem to be directed. They go in one direction only. They are not the same as, if I would show you a film of the things reversed, you would immediately recognize which one is the true film and which one is the reversed film. So there seems to be a directed of things in time, but maybe it's time itself that has a direction. These seemingly simple questions and obvious questions about most fundamental aspects of our world are relevant to anyone who seeks an understanding of the cosmos and our place in it. Yet they are very hard to answer, as it turns out. These problems are all, in one way or another, I think, aspects of the one central problem of the philosophy of time, which I take to be a central problem of much of philosophy, or at least of theoretical philosophy. It concerns the reconciliation of what philosophers have come to call the manifest image, the world as we human beings experience it. The reconciliation with that, the world as we experience it, with the scientific image, the world as it seems to be described and characterized by our best scientific theories. How to reconcile the two is not always obvious, and in particular in the philosophy of time and elsewhere, it constitutes a very central philosophical problem. Just to make this a little bit more vivid, the manifest image is teeming with activity. Objects are booming, buzzing by, changing their locations, properties. Vivid perceptions are replaced by other ones. We seem to be inexorably slipping into the future. Time, or at least our experience in time, seems a very busy and complicated sort of thing. Now contrast that to time as it appears in science, and in particular in physical theories. The little t that we find in the fundamental dynamical equations of physics doesn't differentiate between past and future. It doesn't speed up or slow down. It doesn't pick out a time as the now. It seems to be all there, usually from minus infinity to plus infinity, given to you at once, and that's it. No complicated structure at all. So we seem to have, when it comes to our concepts of time in the manifest image and the scientific image, to echo another debate, an explanatory gap. In order to close this gap, we urgently need the interdisciplinary conversations and indeed collaborations between physicists and philosophers. So I hope you're no longer surprised to learn now that the philosophy department has been involved in the invitation of an eminent physicist to come here to Geneva today to talk about the science of time. So with that, I am very honored and very happy to introduce our speaker today, Professor Fay Dowker. Professor Fay Dowker, she is a professor of theoretical physics at Imperial College London, as it's already been mentioned, and she did her PhD under the supervision of Professor Stephen Hawking at the University of Cambridge in 1990. After that, she did postdoctoral work, first in the astrophysics group at Fermi National Accelerator Laboratory in Batavia, Illinois, near Chicago, then at the University of California at Santa Barbara, and at the California Institute of Technology in Pasadena, also in California, of course. After that, she returned to her native UK and became a lecturer at Queen Mary University in London in 1996, and then joined Imperial College in 2003. She does research, I'm sure she will be talking about that. She does research on the causal set approach to quantum gravity, which is the attempt to bring together aspects of relativity theory with aspects of quantum theory. And she also works on the foundations of quantum mechanics. To close, St. Augustine, in his Confessions, once famously said, "What then is time?" If no one asks me, I know what it is. Usually it's just, check, it's a 7:15. Yes. So you know what time is, but if I wish to explain it to him who asks me, I do not know. Once you start to think, to ask yourself about really what is the nature of time, you realize that maybe this is far from evident. In the hope now of obtaining some insights into the nature of time, I would like to turn over to Professor Fay Dowker, who will be speaking today about past, present, and future, the science of time. Please.
Thank you very much, Chris, and good evening, everyone. So we're going to think about time tonight, and just to get us in the mood, here's a picture of a very beautiful and famous clock. Some of you may recognize it. Some of you may even have been to see it. It's in the National Maritime Museum in Greenwich in the UK, and its name is H4. It's about, it looks big on the picture, but it's about this big. H in H4 stands for Harrison, John Harrison, the designer and maker of this clock. It took him about 6 years to make, and it was completed in 1759. With this clock, John Harrison solved the famous navigational problem called the Longitude Problem. And that's the problem of how the navigator on a ship can tell what the longitudinal position of the ship is if it's in the middle of the open sea after many days and weeks of sailing with no land in sight. How does the navigator tell what the longitudinal position of the ship is? So the way that Harrison and Harrison's clock solves this problem is by being very accurate. It's a very good clock. It accurately measures the time, and in particular, it's very stable, and it accurately measures the time even when being carried upon a ship on a long voyage, suffering many storms and rough seas. Before Harrison built H4, the clocks that were taken to sea were not very accurate. They used to lose and gain time in a random and unpredictable way. So why is it that having an accurate clock, one that's nice and stable and accurate even when carried on a ship, why does that solve the longitude problem? Well, the navigator can do the following thing. The navigator takes the clock, and before leaving port at some particular fixed known longitude, the navigator will synchronize the clock, say H4, with a clock that will stay behind at the port. And the two clocks are both accurate, and they're synchronized at a particular time. The navigator and the ship then leave, and they go on their travels. And at the moment when the navigator wants to tell what the longitudinal position of the ship is, the navigator looks at the clock, H4, and sees what time that's showing, and deduces that that must be the time at the port that was the starting point of the journey. The navigator then, so the local time is known to the local time at the port, the leaving point of the journey is known to the navigator. The navigator will then find out the local time where the ship currently is, just by an observation of the position of the sun in the sky. That will tell the navigator what the local time is at the ship. And those two times, the local time at the starting point of the journey, the port, and the local time where the ship currently is, those two times together will determine the longitude, because those two times will be different, and the difference will tell the navigator how far east or west the ship has sailed. So for example, if the difference in time, if the local time is 6 hours ahead of the time at the port, then the ship will have sailed a quarter of the way around the globe, and so to the east, and so on. So the difference in the times will tell the navigator where the ship is. And this was a solution, a practical solution to the longitudinal navigation problem. Now, there are at least two concepts of time involved in this story. The first is the concept of local time. So time at the port, which is different from the time at the position of the ship. Now, what that means is, we're familiar with that, that's just what we're familiar with time zones and jet lag. So that concept is basically and essentially a geometrical concept. Local time at a particular position on the surface of the Earth is just a statement about what the position of the sun is in the sky at that moment. But there's another concept of time at play here. If you think carefully about how the argument is made, about how to deduce the longitude, the navigator thinks to themselves, well, I have this clock, and I see that it is showing, let's say, 10 o'clock. I know, therefore, that at this very moment, at the port, the local time is 10 o'clock. So to make the argument, the navigator has to deduce from looking at the clock in their hand what the local time, that at that very moment, simultaneously with the navigator looking at the clock, in the port, far away, many thousands of miles away, the local time, the sun is at a particular position in the sky. That is a necessary part of this argument for longitude. There has to be this concept of far distant events being simultaneous, being at the same time. And I'm going to come back to this concept a little later in my talk. So this story shows us how deeply embedded our understanding of time and the development of our understanding of time is in the wider story of human history. And the development of science and physics in particular and its relationship to our understanding of time was brilliantly expounded by Professor Stephen Hawking in his famous book, A Brief History of Time. And Stephen Hawking was my mentor and my teacher, and I formally dedicate this lecture to his memory. One of the concepts that Stephen only touched upon is the concept of the passage of time, and this is something which Chris mentioned in his introduction. So the question of whether time really physically passes or whether it's simply a psychological aspect of, it's a question of psychology, that time doesn't really physically pass, it's just that we experience it as passing. Now, this disagreement is a current and ongoing lack of consensus, and I've chosen a couple of contemporary thinkers to quote to you to show you that this is an ongoing issue, an ongoing debate. So the first quotation I've chosen is from Paul Davies. He's a theoretical physicist. His expertise is in quantum field theory and curved space-time. And he said, the flow of time is an illusion. And I don't know very many scientists and philosophers who would disagree with that, to be perfectly honest. And presumably the explanation for this illusion has to do with something up here in your head and is connected with memory, I guess, laying down of memories and so on. So it's a feeling we have, but it's not a property of time itself. Time doesn't flow. It's part of psychology. And that is disagreed with by the philosopher of science, philosopher of physics, John Norton, who wrote, time really passes. Our sense of passage is our largely passive experience of a fact about the way time really truly is, objectively. the fact of passage obtains independently of us. Time would continue to pass for the smouldering ruins were we and all sentient beings in the universe suddenly to be snuffed out. We have no good grounds for dismissing the passage of time as an illusion. It has none of the marks of an illusion. Rather, it has all the marks of an objective process whose existence is independent of the existence of we humans. Now, this debate about the nature of time is a very long-standing one. As Chris said, questions about the nature of time have been thought about, discussed, pondered since the time that we actually have records of human beings pondering questions. And I've chosen another couple of quotations to illustrate that. And I've chosen a couple of words to pin to the two positions of Davis and Norton. And those two words are being and becoming. So on the side of Davis and of being, we find Parmenides, 250,000 years ago, who said, "What is has no beginning and will never be destroyed. It is whole, still, and without end. It neither was nor will be, it simply is, now, altogether, one, continuous." And on the other side of the dichotomy, there is becoming. So in support of John Norton's view, I've chosen a quotation from a book on Buddhist logic by Shabbatsky. And Shabbatsky describes the Buddhist doctrine of dependent origination as there is no matter, no substance, only separate elements, momentary flashes of efficient energy, perpetual becoming, a flow of existential moments. And I will return to Shabbatsky and this book on Buddhist logic at the end of my talk. But one of the joys of thinking about time, the nature of time, working on it, is that it engages us with these ancient traditions of thought. So one feels a connection with human beings throughout a long period of history have all been struggling with these questions. So it's a current debate. There is no consensus, but from my own personal anecdotal experience and evidence, I would say that Paul Davies is actually right, that the majority of physicists and philosophers who think about such things agree with Parmenides and with him. That, in other words, the position that the world simply is and that time does not flow is the majority view amongst physicists and philosophers. And that's a little unusual because probably the majority view amongst the general population is that, of course, time passes. And so what's the reason for that? Why is the majority view amongst physicists and philosophers that time doesn't pass and that the universe simply is, that past, present, and future events are all equally real? They have the same physical status. Things that have happened in the past, things that will happen in the future, they have the same physical status. Why is that? Well, some claim, and I wouldn't disagree, that the reason is that the current science, our current best scientific theories, support that view. They support the position of being and of the so-called block universe. So here is physicist Sean Carroll, who says, "Modern physics suggests that we can look at the entire history of the universe as a single, four-dimensional thing. That includes our own personal path through it, which defines our world line. This seemingly conflicts with our intuitive idea that we exist at a moment and move through time. Of course, there's no real conflict, just two different ways of looking at the same thing. There is a four-dimensional universe that includes all of our world line, from birth to death, once and for all. And each moment along that world line defines an instantaneous person with the perception that they are growing, older, advancing through time." And it's going to be a major part of my job tonight to explicate this paragraph here by Sean Carroll, the modern science, the modern physics that he refers to is general relativity. That's Einstein's theory of gravity and space-time. It's our best current theory of space and time. And my job, part of my job, is to explain to you why general relativity leads us to this particular view, this view of the universe as a block with past, present, and future events, including my own death, there already in what exists. Now, to do that, I'm going to take a step back from general relativity to first give you the scientific view of space and time that pertained in science before general relativity. And that is the view of Newtonian physics. So I'm going to explain the picture, the world picture that Newtonian physics gives us. And I've called that Newtonian space. So in Newtonian physics, there is the concept of three-dimensional space. Three-dimensional space with objects in that space. So objects like tables, chairs, flowers, planets, spaceships. These are objects, particles, they exist in three-dimensional space, and they each have a position in three-dimensional space at a particular moment of time. So we can choose a moment of time, take a mental snapshot of three-dimensional space, and in that snapshot, everything that exists will have its position in three-dimensional space. I'm going to call that time that you choose, that initial time at which we take the snapshot, 0. So that's the 0 point, the initial time. And I'm going to invite you to envisage that snapshot just laid out there as what I've illustrated here as a two-dimensional slice. Now here we come upon a perennial problem, which is that we're limited in our ability to draw pictures of space-time because it's very difficult to draw anything other than one, two, or three-dimensional things on a two-dimensional screen. So really, this snapshot of the world, of the three-dimensional space with objects in it, should be three-dimensional. We can't draw that. So to stand in for three-dimensional space, I'm just going to draw this two-dimensional space. And these objects in the universe, these are galaxies. This is a picture that I've taken from a picture of the Hubble Deep Field of distant galaxies. So the galaxies are somewhere in this three-dimensional space. This is a two-dimensional picture, remember, of a three-dimensional space. Okay. Later on, let's say an hour later, we take another snapshot of three-dimensional space, and the objects will have moved, some of them, and they'll take up new positions. And I invite you to imagine taking that new snapshot and stacking it above the original one and labeling that snapshot with a number 1. 1 stands for 1 hour. And let's just keep doing that. So another hour goes by. We take another snapshot of three-dimensional space. The objects are in whatever positions they're in now. We take that snapshot and we lay it out above the other two snapshots at a position which I'll mark 2. And we keep going. So here's another snapshot. An hour later, at a position I mark 3. And so these snapshots are all stacked up one above the other in the order in which they are taken. Now, I just chose 1 hour arbitrarily. I could have chosen half an hour, or every minute, or every second. And of course, for each moment when we take the snapshot, you can conceive of adding another one of these three-dimensional spaces. So we stack them up like this, and it is a postulate, an axiom, an assumption of Newtonian physics that for every moment of time, continuously between 0 and 1, there is a snapshot to be taken, and there is three-dimensional space with objects in their positions at that time. So these spaces can be stacked up, and there are infinitely many of them between 0 and 1, infinitely continuously many of them. So if you stack them up, what you end up with is a 4-dimensional block. Remember, what I've drawn here, of course, is just a 3-dimensional block because we can't draw 4 dimensions. These slices are really representing 3-dimensional space. So if you stack up 3-dimensional spaces one above the other, then you'll get an extra 4th dimension, and this will be a 4-dimensional block. You can't draw that, so this is just a 3-dimensional cartoon of what is really a 4-dimensional space-time. So in Newtonian physics, time is spatialized as another dimension. We can conceive of it as a 4th dimension. We can also now study in Newtonian space-time physics, the motion of these objects, the planets, for example, and that was a very pertinent example for Newtonian physics because celestial mechanics was one of the greatest, understanding celestial mechanics was one of the greatest achievements of Newtonian physics. And what we can describe an object like a planet in terms of a world line in space-time. So what's a world line? Well, at the initial time, the planet will have a particular position. So it will be here, say, in space. And then an hour later, it will have moved, and it will be here now in space. And 2 hours later, it will be here in space. 3 hours later, it will be here in space. And at every time in between, it will have a position. So there will be a continuous line of positions in space, joining its initial position here at time 0 to its final position here at time 3 hours. This world line is a full description of what this planet is doing, and all the other planets will also, and other things, you, me, the tables and chairs, will also have their world lines in space, Newtonian space-time. So here's another one. This is an object which starts off at the same position as our planet. It goes off to a different position after 1 hour. It's at a different position at 2 hours, and then it comes back to join the original planet after 3 hours. So these are 2 different world lines, 2 different objects in space-time. We can ask, what is the time that elapses for the planet moving along the red world line? And the time, that's easy to answer, is 3 hours. It takes 3 hours for this planet to do whatever it's doing. And it also takes 3 hours for whatever's following this green world line from this position here to this position here. And that's true of anything that's moving in this space-time. If we want to know how long it takes, we just to do what it's doing, we just take the initial, let's say it starts at the initial, on the initial slice, in the initial space, and it ends up on this final one. However it goes, wherever it goes, however it moves, it will take 3 hours. There is this universal concept of a global time. It ticks away at the same rate for everything in this 3-dimensional space, and it doesn't matter how you move or where you go. So the notion of simultaneity holds in this picture. So in this 3-dimensional space, at this time, 1 hour after the initial time, there's an event here, which is the planet being here, and this other thing, the green thing, being here, and those 2 events are simultaneous. It's the same time for those 2 things in this 3-dimensional space. So that harks back to our understanding of how the longitude question was answered. Okay. Oh, and I should mention that this picture is only a finite chunk of an infinite space-time in Newtonian physics. So in Newtonian physics, 3-dimensional space is infinite. It extends infinitely far in all the 3 directions, and time is also infinite. So as Chris said, really this is just a piece of an infinite space-time, and time really starts at minus infinity down here and goes up to plus infinity up there. So we've just drawn a small piece, a finite chunk of this infinite space-time. So the revolution of relativity changed this world picture to a new view. A new worldview came to pass, it came into being with relativity. And our new view of space-time is an Einsteinian view. It shares, and in this view, space-time, the world, is a four-dimensional space-time. It shares that characteristic with the Newtonian space-time. It's four-dimensional. But there, the difference, the similarities end. I said that Newtonian space-time is made of space. It's this stack of three-dimensional spaces, one above the other, forming the four-dimensional space-time. Einsteinian space-time is not made of space. In fact, in this new worldview of Einstein, of general relativity, there is no such thing as three-dimensional space. That concept doesn't appear at all anywhere in the theory. So if it's not made of stacks of space, a stack of space, what is it made of? What is space-time made of in general relativity? Space-time is made of idealized events where you can think of an event as, for example, a firework, a small firework that explodes. That is an event. It's something which is localized in space. It's a little thing, and it lasts for only it has a short duration, so it lasts for a short amount of time. So it occupies a small piece of space-time. Now we can think of a smaller firework lasting for a shorter amount of time. It's a faster burning firework. That will be an event which occupies a smaller piece of space-time. If you take the limit of an infinitely small firework lasting for an infinitely short time, that is a point event, and Einstein's space-time in general relativity is made of infinitely many, continuously infinitely many such point events. And they are arranged so that the collection of them all is four-dimensional. There is no time coordinate, no slicing of this four-dimensional space-time into three-dimensional spatial slices. There is, however, a notion of past and future. So in the diagram, the past is down here on the diagram, this picture, this world picture, and the future is up here. Again, this is just a finite chunk of space-time that I've drawn. You can conceive of this just being part of a larger space-time. There's no space, but there are world lines still. So here is a world line. The world line is now not made of different positions of an object, but it's made of different events along the world line of the object. So, for example, the event of me having breakfast yesterday could be this event, and me having lunch today, and me having dinner later on this evening, and me flying home to London tomorrow. These could be events along my world line. And it's an axiom of general relativity that in between all those events, there are continuously many, infinitely many other events. So these are all the events along my world line for me, ordered in the order that they occur to me. And everything and everyone, you also, planets, they all have their world lines in space-time. World lines made of the events that are associated with that object. So here's someone who was with me at breakfast yesterday, and then goes off on a different journey through space-time to different places. And we meet at the airport tomorrow. And in general relativity, in Einsteinian space-time, the time that elapses for me along my world line is different from the time that elapses along the world line of someone else. Now, that is true. We don't notice in everyday life, so in my normal everyday life and your normal everyday life, the differences that elapse along our different world lines on the watches and clocks that we carry is not measurable because the differences are so tiny. But if we were to be moving at speeds close to the speed of light with respect to each other, or if we were going off to far-flung parts of the universe where there are black holes and hang around the horizon of a black hole for a long time, then we would be able to detect the differences in the times that elapse along different world lines. And if you've seen the movie Interstellar, the whole premise of that film is that time elapses differently for people who go along different trajectories, different world lines in space-time. So time, physical time, in general relativity, is not a global concept. There is no such thing. There's no such thing as simultaneous events in general relativity. There is space-time, there are world lines in space-time, and time, as we know it, as we understand it, time that actually passes and is physical, passes along world lines only. There is no space, only space-time, and there is no simultaneity. So here's another picture of the block. This is, I've gone down one dimension. So before I had a picture of a piece of space-time that was a three-dimensional depiction of a space-time that's really four-dimensional. Here I've just sketched a cartoon in 2 dimensions of a 4-dimensional space-time. This is the beginning of the universe, if it had a beginning. If it didn't have a beginning, then we have to stretch this bottom part of the picture all the way down to minus infinity. Here's the end of the universe, if it has an end. And in this block are all the events that will happen, that are happening, and that have happened. And let me say that, for example, this star could represent the event which is me being born. And this star could represent the event of me dying. And these are all the events of my life strung out in this one-dimensional world line in space-time. And here's another world line of someone. These blue lines represent photons, for example. So this could be the trajectory of a photon that's produced in some sub-supernova somewhere. It travels through space-time and intersects my world line here. That means that I see the supernova. So all of this exists. This is the concept of the block universe in general relativity. There's no space here, no three-dimensional space, just time passing, time elapsing along world lines. That block view does seem very, very much at odds with my experience, my subjective experience. Of course, you can't experience what I'm experiencing, so I just have to report to you that what it very strongly feels like to me is that I am somewhere right now on this world line. So I'm born, here I die. I'm 52. So say, I live an average life. I'll probably be around here. Okay. What it very strongly feels like to me is that I'm located somewhere on this line, moving upwards on the line. Things are happening, more and more events are happening, and as they happen, as these events happen, my position along my world line is moving upwards. So it's as if there's a very special illuminated spot. And luckily I have my laser pointer so I can actually illuminate it for you. So here we have this spot that's my experience seems to coordinate with an illuminated spot that is constantly and inexorably, unfortunately, because I'm going to get there, right, to my death, inexorably moving upwards. And presumably, I can't experience what you're experiencing because it's subjective, but presumably you all feel the same, right? So if this was your world line, you would feel that, oh, well, that's my world line in general relativity, but I really strongly feel that I'm somewhere on that line right now, moving upwards. That corresponds to my experience, my conscious experience that there is a special position on the line right now. Of course, it's constantly changing, it's moving, but there is a special position. And the thing about general relativity is that there's no such thing in the theory as illuminated dots moving up world lines. Those dots don't exist, and it's a good job they don't exist because it wouldn't make sense. Because if I've got a moving dot along my world line and a moving dot along your world line and all the other world lines in the universe as well with moving dots along them, then there would be no way to coordinate where those dots should be. So if my dot is here, where's your dot? There's no way to answer that question. And so those dots just aren't there in the theory, in general relativity. There's no way to make this block universe view correspond to our subjective experience, I claim, right? However, there's disagreement about that. There's difficulty in communicating amongst scientists and philosophers. And here's a conversation which I claim I've had many times with other physicists and with philosophers that show that there's just a mismatch in understanding and communication. So thinker A and thinker B are having a discussion about the block universe. Thinker A says, well, things happen in the block. There's a tree growing. There's a supernova exploding. There's a person experiencing time passing there in the block. Thinker B says, no, the block is static. It corresponds to events having happened, not to them happening. There in the block is the history of the growth of a tree. There is a supernova having exploded. There is a person having experienced time passing. A says, no, yeah, the block does correspond to events happening. B says, no, it doesn't. Yes, it does. Right? And it's a debate that's going nowhere. This, I think, this disagreement, this lack of understanding, this lack of comprehension cannot be resolved within general relativity, I believe. I think that within general relativity, it's as far as you can go to just take one of these positions, and one cannot hope, actually, to persuade another person who has the contrary position. Now, I should come clean here and say that I side with thinker B. I side with John Norton and with the Buddhist philosophers, that time does pass. It's a physical process, I believe, and that general relativity does not do justice to it. And at this point, we will, in my talk, I'm going to leave the shores of known physics, and if you like, we'll now go forwards and speculate about the future. So I've covered time in the past, that's time as we understand it in Newtonian physics, time in the present, that's time as we understand it in general relativity, and now I'm going to speculate about time as we might understand it in the physics of the future. To do justice, which I would like to the temporal nature of our perception, whilst maintaining the four-dimensional nature of the physical world in general relativity, what seems to be required, what seems to be called for, is a growing block, not a static block, one that just exists once and for all laid out, past, present, and future, but a growing block and a process of becoming for space-time, one in which the past is fixed and concrete, but the future has yet to happen, has yet to become. And it's this notion of a growing block is associated with the philosopher C.D. Broad. So this idea has been a fruitful and useful heuristic in developing one approach to the problem of quantum gravity. That approach is called Causal Set Theory. and Chris in his introduction mentioned the problem of quantum gravity. General relativity is a superbly successful theory in its sphere of application. However, it has a problem, and that problem is that in general relativity, one has to assume that matter is deterministic, that it follows deterministic laws of motion. However, we know that matter at its most fundamental level is not deterministic. It doesn't behave in a deterministic way. It's quantum mechanical. And one of the features of quantum mechanical behavior is that it's unpredictable. You can't know for sure what the outcome of a quantum experiment is going to be. You can make probabilistic predictions, but you don't know which of a certain set of outcomes is going to occur. So we do not know then how quantum matter gravitates. We only have a theory of gravitation for matter that's deterministic. We don't have a theory of how quantum matter that's behaving truly quantum mechanically, how it gravitates. What's its gravitational field? How do we describe how quantum matter, the gravitational interactions of matter that's truly quantum? We do not know. That's the problem of quantum gravity. There are many different approaches, and I work on one called Causal Set Theory. And in the remainder of my time tonight, I'm going to briefly tell you a little about Causal Set Theory. So the basic idea behind Causal Set Theory, and remember this is speculation about a theory that might yet come to be in the future. Space-time is not smooth and continuous, but bitty, granular, pixelated, or atomic. So just as we understood matter not to be smooth and continuous, but actually made of atoms, that, for example, a metal block, if you try to divide that metal block in half and then in half again and then half again and half again, you can't do that infinitely often. Eventually, you reach the discrete atomic structure of the metal, and there are atoms of the metal that can't be divided anymore. So space-time, this four-dimensional space-time of general relativity, is also not infinitely divisible. You take a piece of space-time, you divide it in half, and divide that in half. Eventually, you get down to events which are fundamental and indivisible, and we call those space-time atoms. So the idea is to propose, behind causal set theory, is to propose that space-time comprises these atomic units of space-time atoms. But what binds these space-time atoms together? What keeps them from just falling into a heap of dust? What gives the space-time formed of these atoms structure? Here we looked to general relativity for an answer. Space-time in general relativity has a causal order. The events of space-time in general relativity are causally ordered. That causal order is fundamental to understanding general relativity. And what it means is that some events can causally influence other events in space-time, and some events can't. So here I've drawn a pattern of causal relations that exist. And the rules for which events are causally related to other events is whether that event can send a signal to the other event. So this event here, which I've called D, is to the causal past of this event A because it can send a photon along this blue line to A. So this event D is causally related to A, it's in the causal past. This event C is in the causal future of this event D because D can send, say, a spacecraft or a space shuttle along this red world line to C. But some events are causally unrelated and there's no possibility of either of them influencing the other. So C cannot influence A. And the reason is that things can't travel faster than light. So if C were to send something to A, that something would have to travel faster than light. And it can't, and so C is causally disconnected from A. And there's no sense in which C comes before A or A comes before C. They're just unordered. They have no causal relation to each other. And this is true of any pair of events in space-time in general relativity. They're either unrelated to each other and can't influence each other, and there's no order between them, or one is to the past of the other. So we take that and we add it to our hypothesis that space-time is made of discrete space-time atoms, and we endow those space-time atoms with an order. So here are the space-time atoms represented on my diagram by these dots, and these arrows just represent the order, the causal order that these atoms have. So D precedes C. D also precedes A, which precedes B. But C and A have no arrow between them, and they are causally, they are unordered. There's no sense in which C comes before A or A comes before C. They just have no order. There's no ordering. And this hypothesis about the structure of the underlying discrete structure of space-time was made independently by 't Hooft, by Meerheim, and by Bombelli, Lee, Meyer, and Sorkin, and has been championed by Sorkin, Raphael Sorkin, particularly. So causal sets are the marriage of atomicity and causal order. Here's our causal set again, made of these space-time atoms with the causal order between them. It's a very small causal set. If our hypothesis is right, then the number of space-time atoms that you would need to describe a universe, our observable universe, is rather larger than this. It's 10 to the 240, roughly. Our hypothesis is that the continuum space-time of general relativity is an approximation to a discrete reality, just like the fluid description of water is an approximation to the true molecular structure of water. And the hypothesis is that these space-time atoms come into being in a continual random process of births. So each space-time atom is born, and the order in which they are born is their causal order. So D is born before C, D is born before A is born before C, but there's no fact of the matter about whether C is born before A or A is born before C. They are unordered in their births. This order is not linear, but it's a partial order. This model in which the universe this discrete universe comes into being has been called asynchronous becoming by Raphael Sorkin. And in this model of the universe, there are two types of physical thing. One type is the space-time atoms and the order relations between them. The other type of thing, and that's the material of our four-dimensional world. The other type is the process, the birth process in which the elements come to be. Both these things are physically real, and you need both. And what corresponds to things happening is the process. The atoms don't correspond to things happening. It's the process in which they're born which correspond to the occurrence of events and to the passage of time. That, at least, is the proposal that is being made in causal set theory. So here's the conversation again. Thinker A and thinker B, they have the same disagreement. This is just a repetition of what we had before. A says, well, the block does correspond to event happening. Now, B has something to hang their argument upon now. B says, well, in causal set theory, there are not just the space-time atoms that make up events, but there's the birth process as well. And it's the process of coming into being that corresponds to happening. And this is what is missing in the block. And this is what correlates with our subjective experience of the passage of time. An event corresponds to a collection of space-time atoms with causal relations between them, but the occurrence of the event corresponds to the birth of these atoms. So I've presented to you if you like, time in the past. That's Newtonian time. Newtonian space-time is about space. And time in the present, our very best understanding of space-time. That's Einsteinian space-time. And Einsteinian space-time is about events. And I've shown you a glimpse, a vision, perhaps, of future physics in which time is not about space, it's not about events, but it's actually about process. So let me return now, as I promised, to this Shabbatsky on dependent origination in Buddhist logic. So again, there's no matter, no substance, only separate elements, momentary flashes of efficient energy, perpetual becoming, a flow of existential moments. And he adds, something must explain how the separate elements of the process of becoming are holding together to produce the illusion of a stable material world. And the Buddhist philosophers proposed that what holds these events, this becoming process, together are causal laws. Now, whether or not the Buddhist philosophers 2,500 years ago anticipated causal set theory, we can debate. But I think this illustrates that we should look to all of our intellectual heritage to get the best possible toolkit in order to make progress in fundamental physics and in philosophy. We shouldn't limit ourselves to any particular tradition of thought, but look most widely at all of human thought in order to give ourselves the best chance of making progress in the future. And I will end there. Thank you very much for listening.
Thank you very much for this very, very lovely talk, very insightful. I hope now that we have at least pushed back some of the mysteries about the nature of time a little bit further. Now we have an opportunity to ask questions to the speakers. And if you would like to ask a question, please try to get my attention, and I will then send somebody with a microphone to you. So who would like to have a question? Here's the first question.
Good afternoon. I'm not so familiar with the causal set theory, but I understand, tell me if I'm wrong, from what you said, that causality has a fundamental nature in the theory. If that's true, if my understanding is true, my question would be, what do you think of the thought experiment of John Wheeler regarding the delayed choice experiment, which was confirmed by Alain Aspect in the 1985, I believe, proving that along the decoherence process, one could affect the duality between wave and particles after that process has occurred, suggesting some people to talk about retro-causality, and even leading the great mathematician Alan Cohn in France, talking about the past that is still moving. That experiment showed that, suggests that some people say that the future is actually dictating the present. I would like to have your views on this. Thank you.
Yes, thank you for the question. That's a brilliant question. There are so many things to say about that. One thing is to just say that all discussions of causality as in as far as quantum theory goes, are hampered by our lack of consensus about what is really going on in a quantum system. So, on one view, if one is doing a quantum experiment, let's say in a box over here, then one should not even talk about or think about what's going on inside the box. All that one is doing is setting up some equipment outside the box in some way, and then recording what that response of the equipment is. So, in fact, there's no sense in which we can say what is happening inside the box as far as the quantum system is really concerned. Okay, so that's actually that's a view that some people take. We shouldn't discuss what's actually going on inside the box. Well, we can't or we shouldn't. So it's very difficult, and there is no consensus on what people call the interpretation of quantum mechanics. The answer to the question, well, how should we think of, what picture should we have of the quantum world? Given that situation, it's extraordinarily difficult to make conclusions about causation, what is causing what to change, when one is trying to talk about a quantum system in a situation in which there's no scientific consensus about how to talk about it, whether we even should talk about it. So that's a sort of caveat. However, the sorts of experiments and thinking that you refer to are indeed an incredibly important aspect of trying to make the physics of causal set theory quantum. The dynamics that I alluded to, in which the causal set elements are born in a partial order, so far all we have is a classical model, which is not quantum, a classical model of how that can happen. So we would like a quantum model, and we would like it to respect relativistic causality. We would like that. The question is, can we do it in a way that is not in contradiction with experiments like the Bell experiments and the experiment you referred to, and in such a way that there is a notion of relativistic causality, but that begs the question, what is that notion of relativistic causality in a quantum theory? So part of our theoretical program is to try to formulate a condition of quantum relativistic causality which allows violations of the Bell inequalities and therefore is not into contradiction with experiment, and yet is in some suitable sense yet to be discovered and formulated, causal. We're not nowhere near there yet. But it's absolutely a crisis point that is a very fruitful place to look very carefully. So it's very important for us, yeah.
Thank you. There was a question over there.
Thank you. Thank you very much for this fascinating presentation. I've really enjoyed your comments at the beginning, defining being and becoming. And being could be compared to space, and let's say physical space, and becoming matter. And matter is, as you rightly said, evolving constantly like complex adaptive systems. So couldn't we say that actually we are a combination of two timelines, two linearities, one defining who we are in a certain space, but also who we are in the definition of matter evolution. And maybe this will, let's say, combine to define time at a certain space, matter, time.
That would be difficult to realize within general relativity because there's no such thing as three-dimensional space in general relativity. So what you're proposing can't be compatible with general relativity. Whether or not future physics will somehow come back to this pre-relativistic notion of there being three-dimensional space, we do not know. Myself, I would strongly suspect not. So my own view of the progress of science is that you just don't go backwards. At least as far as I can tell in the history of science, it's never the case that you go back to, a previous point of view. So general relativity rules out such an idea, but of course it is possible that in the future three-dimensional space will make a comeback, and then perhaps something like what you're proposing could be developed.
We have time for one more question. There's one here. No?
There's just so many jokes.
One of the big arguments of that the time is flowing in one direction is that some events doesn't seem to be irreversible. And my question is, based on what you said tonight, is it because some events seems to be irreversible because the quantum atoms that you spoke about are, after the realization of the events, dispersed in space-time? I don't know if I'm clear.
I think there were two questions there. So I think you're asking about the arrow of time? Is that
Yeah.
Okay, good. So in this process of becoming, there is inherently a direction. So in the sense that, and it just distinguishes the past, which is real, those are the space-time atoms that have already been born, and the future, which is open and that doesn't exist yet. So, and the space-time atoms are born, so space-time grows, it accretes more and more space-time events. And that's directional, that's inherently directional. It breaks, there's no symmetry between past and future there, in that sense. What you refer to as, however, it could be the case that there is what people call another notion of time reversal symmetry is that how Chris described it, if you run a movie forwards and run a movie backwards, then you can tell which one's the right way, right? So eggs smash on the floor and break, but they don't gather themselves up off the floor and reconstitute themselves. So it might be that the space-time that grows via this process of becoming, once you have it, is actually symmetrical. So in the sense that once you have it, the whole thing, from the beginning of time to the end of time, and you run it backwards, that's also a perfectly good and possible space-time. So it could, even though the birth process has a direction, it might be that there's also that there could be a sense in which the dynamics is time reversal symmetric. So the arrow of time and this fundamentally physical process of becoming, which has a direction. Those are sort of they're logically distinct questions. I don't think I understood your second question. That was.
Yeah. No, it's okay. You answered it already. Thank you very much.
Okay.
Because there was a question here, down in the center. Here? Yes.
Hi. The first time, thank you so much for this presentation. It's very great. Second time, I'm sorry just about my question because I learned my first English lessons like 5 weeks ago, and it's quite complicated for me to translate my reflection. So you talk in an example when you're talking about the two people coming together. Did you remember this? You know, about the dimension, and you talk about the event happenings. And my question is, what kind of events? The events, I'm sorry, just event we see, or the events happening and that you do not see? If my question is clear.
Which are you asking about? The events that comprise space-time, a space-time in general relativity?
I guess yes, because you know you talking about the event, but the event we see or we don't see.
Well, I mean, general relativity gives us a worldview of the entire universe, including events that we don't see directly, or that are too distant from us, so that their effects can't be detected by us. So yeah, the worldview of general relativity is a cosmological view. So the space-time is the entire physical world in general relativity. So that will include events that we see, and also events that we don't see. I'm not sure I answered your question very well. Okay.
So thank you very much. We've come to the end of this talk. Please join me once again in thanking Professor Fay Dowker for her wonderful talk.
My pleasure.